cleansing action of soap. So how soap and detergent molecules work, we will see now. To remove the dirt or grease from any surface or our clothes during washing. Soap or detergent, first we dissolve it in water, and in soap and detergent this type of surfactant molecules are present. So here this spherical part, that is actually polar, and the tail part, that is non-polar. So grease, which is non-polar in nature, and surface area on which these grease are attached. Okay, now these molecules, the tail part, that will be attracted towards grease, because this blue region, it is actually water. So the spherical part, that is the polar part, that will be attracted towards water. So that is the reason when these surfactants, they are now adsorb on the surface of grease, these spherical parts that are present towards water side. So surfactant ions orient themselves in grease and water in this fashion, not the opposite direction. That is not the tail part towards water, because tail part is non-polar, it cannot interact with water. Then agitation begins to separate grease from surface. So as a result, what happens? In this way, they surround these surfactant molecules, they surround the grease, and ultimately it is removed and this type of micelle is formed. So here cleansing process, that is complete. Fine. So in these micelles we can see that the spherical parts that are towards water side, because this is water, and grease, which is non-polar in nature, the tail part, that is interacting with the grease part. Okay, so in this way the cleansing action of soaps, it occurs. Okay, now as we have seen how the micelles are formed, but when micelle will be formed, that we have to know. Okay, and that is known as critical micelle concentration. So critical micelle concentration of a surfactant is that value at which the solution property of the molecules shows an abrupt change. Okay, so what is CMC? That we have already seen in the last class, that is the concentration at which micelle will start forming. Okay, so there is a particular specific concentration of the specific concentration of the surfactant. If the concentration is above that value, then only micelles will be formed. Fine, and that concentration is known as critical micelle concentration. At this concentration, the physical properties of the solution, there will be abrupt change. Okay, now why this abrupt change? Because above CMC there will be only aggregated large particles of colloids, that is the micelles, but below CMC there is no micelles. So as there is different size of particles below CMC and above CMC, so that is the reason that there will be abrupt change. So generally for surfactants with hydrophilic head group, when it is same, so suppose we have taken two different surfactants where the spherical polar part, that is same, that is the head part, but in one case the tail part and the another molecule, the tail part, these two tail, they are having different chain length. So in that case what will happen? The CMC will be less for that surfactant which is having larger carbon chain length. Okay, so when tail part is very long, then CMC will be decreased. Okay, that means at a lesser concentration we can easily get micelles. Fine. Now above CMC, as we have mentioned that physical properties of the solution will change. So here surface tension of the solution, if we consider, it will be constant after CMC, because now the interfacial surfactant concentration, it has already reached the saturation point. So further adsorption is not possible. As further adsorption is not possible, So no question on the that it will affect the surface tension. Okay, but before CMC, as that is below CMC, as we are increasing the concentration, surface tension, there will be some change. But once CMC is reached, there will be no change in the surface tension, so it will be constant. Now if we look at this graph, you can see surface tension is gradually decreasing before CMC is reached. But once CMC is reached, this is the CMC region. After that point, there is no change in the surface tension because now the surface area is fully covered, saturated. Okay. Addition of simple electrolyte in ionic micelles also decrease their CMC. Okay, so these are the very little informations that you should know, because there may be some options given that whether this statement is correct or not. So these informations are important from that point of view. So when we are adding electrolyte in ionic micelle, then also CMC will decrease. Okay, so CMC will decrease with increasing chain length provided head group is constant. Then also CMC will decrease, and in case of when we are adding simple electrolyte, that will also decrease CMC. So here we have already seen surface tension, how it is changing. Then turbidity, see, after CMC it is abruptly increasing. Now it will happen because after CMC that is actually colloid. So micelles are there, aggregated particles are there. So there is colloid now. So obviously turbidity will increase. Now it is no longer, it will appear as transparent. It will be turbid. Okay. And in case of molar conductivity, see how it is changing. Before CMC it is gradually decreasing, but after CMC the decrease is very abrupt, very sharp, right? Now the reason is, when concentration is gradually we are increasing below CMC, as concentration is increasing, so obviously mobility will decrease. So that is the reason molar conductivity will decrease. And when CMC already reached, now the number of particles highly that is abruptly decrease, because now there will be only micelles. So number of particles are large, but number of these particles are now decrease in number. So individual particle, if we consider, the number is decreased, so obviously conductivity that will also decrease. And then we have voltammetry. This is the nature of change. So this graphs, that is the nature of these properties, it is important to remember because graph related question may also be there. So then if you have to choose which relationship is correct, that is, suppose any of these physical properties given, how it is behaving below CMC, above CMC, this type of questions you can answer if you know how it is changing. Then we have osmotic pressure. When concentration we are gradually increasing, this is colligative property, so obviously with increase in number of particles it will increase. But see, once CMC is reached, now there is no further change, because now micelles are they have started forming, right? So the value is no longer increasing because number of particles are not increasing further. It has already there is formation of aggregated particles. So that is why osmotic pressure, it is almost constant. Then conductivity of solution having surfactant molecules decrease sharply at the CMC. For each surfactant there is a specific temperature, okay, and that temperature is known as craft temperature. So formation of CNC can take place only above this temperature. So remember this term, craft temperature. Fine. And for each reactant, as the system temperature increases, CMC initially decreases and then it is increasing. Fine. So remember all these processes. Initially there is a decrease and then it will increase. So this is the relationship with temperature. Now we have seen how surface tension is changing, but if we want to know that how it is actually happening, that is how does surfactant decrease surface tension. Okay, so here we can see water bead without the addition of surfactant. So when it will fall on any surface, there is pore wetting. So it is the water droplet, it has spherical type of shape and it is not spreading. That means here surface tension is high. Now once we have added some surfactant to the water and then we are having this drop of water, now see the spherical nature, it is lesser now, that is in case of surfactant added water. So now the spreading will increase and now the wetting is not poor. Okay, so water bead with addition of surfactant, now it is good wetting, it can spread, and the reason is surface tension is lowered. And the reason for reduction in surface tension when we are adding surfactant molecules is that these surfactant molecules, it will absorb and the water surface. Okay, now the surfactant molecules, obviously it will replace some of the water molecules in the surface. So suppose if it is the surface of water, when surfactant molecules will be present here, so they will replace some of the water molecules from the surface, right? And the forces of interaction between surfactant molecule and water molecule. So suppose there is a surfactant molecule and water molecule. So the interaction between them and the interaction between two water molecule by hydrogen bonding, that is always more. So the forces of attraction between surfactant and water molecules, they are less than those between two water molecules. So when you have not added surfactant, there is only water molecule. So there will be water-water interaction only. But when surfactant is added, some of the water particles from the surface area will be removed and that place will be taken by surfactant. And there will be now interaction between surfactant molecule and water. Now this interaction is less, so that is why now the contraction force, that will also reduce. As a result, surface tension, that will also decrease. Okay, so now it will spread more. So wetting property, spreading property, all these will increase when we have added surfactant to water. We have a question here which is related to how CMC is dependent on the form, that is with some physical properties. The ions of surfactant molecules undergo association to form clusters. Now this statement is obviously correct because we have seen when we have discussed classification of colloid molecules, okay, depending on the nature of the particles of dispersed phase. In that discussion, the last part is the aggregated particles, that is how micelle is formed. So here micelles are basically formed by surfactant molecules when large number of surfactant molecules are associated together to form cluster, and these clusters now they will have dimension of colloidal particles. Okay, so these clusters are actually known as it is known as micelles. Okay, so at critical micelle concentration, obviously micelle formation takes place because below CMC it doesn't take place, right? So the first statement, that is actually correct, true. It is multiple corrected, so more than one may be correct. Turbidity of solution increases abruptly. Now this we have already seen in the graph. That is just we have discussed that how turbidity is increasing suddenly, and the reason is because after just CMC is reached, colloid formation is taking place. So obviously turbidity will increase because now it is not transparent, it is turbid, because it will not have property like true solutions. True solution, it is always transparent, but now gradually it will be towards translucent. That means turbidity will increase. So this is also correct. Substances like grease, fats, etc. dissolve colloidally. So obviously at CMC they will dissolve colloidally because only at CMC and above CMC micelle formation is possible, that is colloid formation is possible. Okay, so this is also true. Last statement, colligative properties increases suddenly. Now this is not true, because after CMC or at CMC, number of particles are reduced, because now individual particles, they are associating to each other and they are forming clusters. So number of particles reduced means colligative property that will also decrease. Okay, now the reason is because colligative properties, it is not dependent on the nature of the solute, it is dependent on the number of particles that is present in the solution. So if number of particles are less, so obviously this colligative properties, that will also be less. So we cannot say that it is increasing suddenly. So this statement is not correct. So here correct statement is multiple correct choice A, B and C, not the last statement. We have a problem here. So the problem is integer type. Solution of palmitic acid. So this is a type of fatty acid. Molecular weight given 256 gram per mole. It is taken in benzene. So you can understand, as there is non-polar part in this type of fatty acid molecules. So they will be they can dissolve in benzene, because benzene is also non-polar. And here 4.2 gram of the acid is present per liter of benzene. So as if you know now the concentration, fine. This solution we are pouring on the water surface, and it forms a monomolecular level of this acid. Okay, monomolecular level, that means only one molecules are present in the level. Now benzene, when it will be evaporated, its boiling point is not very high. So when it will be get evaporated, then actually this surface layer is formed on the water. Okay, if 500 centimeter square area of water surface is to be covered by the monolayer of palmitic acid, then the volume of the solution in benzene that will be required is y into 10 to the power minus 6 liter. We have to find this value of y to nearest integer. And here another information is given. Area covered by one molecule of palmitic acid, 0.21 nanometer square. See, the value is so small, it is in nanometer unit, because for one molecule the surface area, obviously it will be very small. Okay, so what are the informations given? The amount of this fatty acid in benzene, what is the amount, and in how many ml that is present, that is given. 4.2 gram in 1 liter of benzene. Okay, now we are pouring this on water surface, and after this benzene will be evaporated, and there will be only palmitic acid on the surface of water, and they are forming monomolecular level. Now on this water surface, suppose 500 centimeter square area of water surface we want to cover by monolayer. Then what is the corresponding volume of solution in benzene that we have to add it. That is, when we are pouring the benzene solution of palmitic acid, what volume we should actually pour on the surface, that we have to find. So we have to find out y. Now 0.21 nanometer square, we will convert it to centimeter square, and this is equal to 0.21 nanometer to centimeter. If we want to move, we have to multiply with 10 to the power minus 7, but as it is surface area, there is square, so it will also be 10 to the power minus 7, it will be actually minus 14. So the value will be 10 to the power minus 14 centimeter square. Okay, so this is the volume conversion, area conversion for one molecule of palmitic acid. Next we will find out that to cover 500 centimeter square area, what should be the number of particles required, because one particle is having area 0.21 10 to the minus 40 that we have just calculated. So one molecule can cover this area. So to cover 500 centimeter square area, what should be the number of molecules? How we can find that? We have to divide 500 by this value that we have just obtained. So 0.21 10 to the power minus 14 centimeter square area, that is covered by one molecule. So if we want to know the number of molecules to cover 500 centimeter square, this will be equal to 500 by 0.2 10 to the power minus 4 number of molecules. This is equal to 2.38 10 to the power minus 17 molecules. Now in each step you can actually get some idea whether you are doing it correctly, because when it is number of molecules, obviously the number will be very high. Okay, so suppose you are doing any mistake and you are getting 10 to the minus 17, be very careful that it cannot be negative, right? So that's why I have just written the negative sign and then I erasing it. Okay, so the number of molecules, it will be very high, so the value should be like this. Next, what we will do, we will find out what will be the number of moles in this amount, because molecular weight is given. So number of moles in 4.24 gram palmitic acid is given mass 4.24 divided by molar mass, and this is 0.016 moles. Now 1 mole contains Avogadro number of molecules, so 0.016 moles will contain 0.016 into Avogadro number of molecules. Now this number of molecules, or you can say 0.016 moles, that is actually present in 1 liter of benzene. Okay, so now we know what is the number of molecules present in 1 liter of benzene. So we can easily calculate that this number of molecules, it is present in what volume of benzene, right? So 0.016, this is the number of moles. So number of molecules will be 0.016 Avogadro number Na. So this number of molecules present in 1 liter, and we will do the calculation in liter because answer is in liter. So this number of molecules present in 1 liter, 2.38 10 to the power 17 molecules will be present in 1 divided by 0.016 Avogadro number 6.023 10 to the power 23 in the numerator 2.38. Okay, so this will be the final calculation and it will be 24.7. You will directly get 10 to the power minus 6 because 10 to the power 17 here and we have 23. So 17 minus 23, it is 6. Okay, and see the format of the final answer, that is also y equal to 10 to the power minus 6. So this is the value of y. And if we want to express it to nearest integer, it will be 25. 24/7. So final answer you have to choose depending on what type of instructions are given in the question. Okay. So this is the actual volume. So the volume, obviously it will be very less and it is in liter unit. So the value should be very less and y is around 25. Here we have picture A, B, C, D. Identify correct molecular picture showing what happens at CMC of an aqueous solution of surfactant. This spherical region, it is the polar head, and the tail, that is non-polar. And this small black dot, that is water molecules. So in picture A, remember we have to find that picture which will resemble critical micelle concentration formation. So there must be formation of micelle. So if you consider picture 1, there is no micelle, right? So this cannot be the picture to show what is happening at CMC. In in picture B also, and in the first picture there is another thing that you can notice, that this tail part that actually remains in this way. Sorry, this part is okay. Okay, in the first picture the only error is that is present, there is no micelle formed. In the next picture, see, 3 molecules are there, but we cannot say this is micelle. This is not micelle, right? And also here orientation of the surfactant molecule, that is not correct. Next, in case of C, now see this spherical part, it is protruding from the surface, but they should remain towards water side because water particles are here and these parts are polar, so obviously they should face water particles, but that is not the case. So though here we have micelle in this picture, but the direction of the surfactant, that is not correct. And in the last one, here the directions are correct and also there is micelle picture. So D will be the correct picture, and D is present in option 1. Okay, so in this way we will choose the correct answer. (0.27) of a long chain fatty acid. So just like this palmitic acid, the problem we have solved, it was dissolved in 100 centimeter cube of hexane, that is 100 ml actually, ml and cc same. Now out of this 100 we have taken 10 ml of this solution and we have added it drop wise to the surface of water. Now this water is taken in round watch glass. Okay, watch glass, it looks like this, round watch glass. Hexane evaporates and monolayer is formed. So we have dissolved it in 100 ml hexane, this amount of fatty acid, and hexane is just like benzene non-polar, okay, organic solvent. So obviously this non-polar part of fatty acid, because of the presence of non-polar part of fatty acid, it will be easily dissolved in hexane. Now after this addition drop wise on the surface of water, hexane boiling point is very low, it will be evaporated and only there will be this fatty acid molecules remaining on the surface of water. So monolayer is formed. Another information given, the distance from the edge to the center of the watch glass. So if this is the center, this is the edge, this distance is given, which is 10 centimeter. Now this distance is nothing but the radius, right? So it is not directly mentioned in the question, it is mentioned in indirect way, edge to center, okay, but actually it is radius. We have to find out what is the height of the monolayer, okay, though the height is very small. So suppose if there is water, this is water surfaced and the monolayer is formed like this, this is water part. So this height of this monolayer, that we have to find. And here some more information is given, density of fatty acid, gram per centimeter cube unit, pi value given 3. Pi actually we write 22/7, but it is close to 3. And all the options are given in meter unit. So the height that you will find out, that should be in meter unit. Okay. So here we have centimeter, but we have to do the unit conversion. Here we have a picture of a volume of cylinder formula, how we are getting it. Okay. Now why we have mentioned it, because when you will find out this height, basically you have to take the help of this formula. So as if this is a monolayer and this height you have to find out. Now this R value, that is actually this 10 centimeter, okay, because the layer will be formed on the surface of water and water is present in watch glass. So here we have to know what is the volume formula for cylinder type of shape. Okay, so 100 centimeter square, sorry, centimeter cube, it is actually 100 ml. So 100 ml contains 0.27 gram, but we have taken only 10 ml. So in 10 ml the amount will be 0.027 gram. Fine. Density of fatty acid is given, and we know what is the mass of 10 ml. So you know volume, sorry, 10 ml of the solution, but in this solution there is both presence of fatty acid as well as hexane. So we cannot say this is the volume of fatty acid, this is volume of fatty acid plus hexane, but we know the mass of acid. So this is the mass of fatty acid. We know the density. So from the formula of density equal to mass by volume, we can easily find out what should be the corresponding volume. So volume is m by d, mass by density, 0.027 gram divided by density given in the question, 0.9 gram per centimeter cube. Gram will be cancelled and the value is 0.03 centimeter cube. So now you know what is the volume of this long chain fatty acid which is present in 10 ml of hexane solution. Now this volume is actually the volume of pi r square h, and you have to find out h because here r is known, volume is also known. So using the formula pi v equal to pi r square h, here v is known, pi is 3, r is 10 centimeter, v 0.03 centimeter cube, and h is unknown. So what we will do, h is equal to v by pi r square, 0.03, pi value is 3, you have to use that value which is given in the question, and r is 10. So after calculation it will be 10 to the power minus 4 centimeter, but you have to convert it to meter because options are given in meter. So if you directly see, if you miss this step, you will think that correct option is 10 to the power minus 4, but 10 to the power minus 4 is correct only when it is in centimeter. So we have to convert it to meter, and centimeter to meter if we want to convert, we have to multiply with -2. So ultimately it is -6 meter. Correct option, last one. Okay. (10 ml of 1 millimolar surfactant solution). Millimolar, not 1 molar. It forms a monolayer which covers 0.24 centimeter square on a polar substrate. Not necessarily water, it may be any polar substrate. Now there is polar head for the surfactant molecules. Normally we take the shape as spherical shape because it is polar head. But in this case we will approximate it as if it is a cube. So what will be the edge length of that cube? Options are in nanometer. Here normally we are habituated to see this type of polar head, right? But suppose if it is not like that, if it is a cube, that is also possible. Now cube means all these lengths are same. Now one of the, that is this surface area, that will be attached to the polar substrate. So suppose the polar substrate, the surface is like this. So here all the cubes, they will be absorbed like this. Okay, these are actually cubes. So one of the surface that will be absorbed on the surface. So suppose this is the colored coloring this part, that will be absorbed on the surface. So suppose if I have drawn here 3 surfactant molecules. So this type of square surface area, this is actually the surface area of a square, we are not taking all the faces of cube, we are taking only one face. So this is actually the area of square. So this total area that is given, fine, and you know what is the concentration of surfactant solution. That means you can easily find out what will be the number of surfactant molecules, okay, from this concentration. Now if you know the number of surfactant molecules and if you know what is the total area of coverage, then you can easily find out what will be the total area of these surfaces. And if you know this, you can easily find out the edge length. Now look at this picture. This is cube, okay, but we need area of only one face, and as it is cube, the edge all are same, so area formula for this square is a square. So this is actually the formula for area of a square. Now first we will find out what is the total number of surfactant molecules. 1 millimolar, that will be equal to 10 to the power minus 3 molar. Now 1000 ml, that is 1 liter contains 10 to the power minus 3 number of moles. But here we have only 10 ml. So 10 ml will be 10 to the power minus 3 divided by 1000 multiplied by 10. 10 to the power minus 5, that is the number of molecules. Now polar head of 10 to the power minus 5, this is actually number of moles, but the corresponding number of molecules will be 10 to the power minus 5 into Avogadro number. So polar head of 10 to the power minus 5 Na number of molecules covers area 0.24 centimeter square. Okay, so for one molecule, what will be the corresponding cover, that we have to find out. 0.24 divided by 10 to the power minus 5, Avogadro number value, (4 into 10 to the power minus 20 centimeter square). Obviously the unit will be square because this is number of moles and here unit is square. So for this number of molecules, area is very large, but now the area for one molecule, obviously it will be very small value, 4 into 10 to the power minus 20. Okay, so this is the area. So this value is actually equal to a square. So a is the edge length, a square is equal to the area because it is for one molecule. So for one molecule, one of this face area, that will be 4 into 10 to the power minus 20. Now here calculation is very easy, it will be 2 into 10 to the power minus 10. Now it is centimeter unit, and centimeter picometer relationship is 1 picometer is equal, or I can write 1 centimeter, that is equal to 10 to the power 10 picometer. Okay, that means 1 picometer will be 10 to the power minus 10 centimeter. So here we have 10 to the power minus 10 centimeter. Just remove this part, so it will be 2 picometer. So this is the edge length. Sorry, it is in two types of units are there, nanometer and picometer. So we are getting it in picometer because this is the relationship of between centimeter and picometer. Okay, so 2 picometer. This is the answer. That means correct option is option 3. Okay. Next, we will discuss some physical properties of colloids. First point, heterogeneity. So, when we have compared true solution, colloidal solution and suspension, there we have already seen that suspension and colloid, these two are both heterogeneous in nature. Only true solution is homogeneous in nature. So, here presence of two phases must be present. Since colloid consists of two phases, so continuous dispersion medium and discontinuous dispersed phase. So these two are the two phases. They will be obviously heterogeneous in nature, because when we talk about homogeneous, there will be only one phase, but here we have two phases, so it will be heterogeneous in nature. Visibility of dispersed particles. Now it is true they are heterogeneous, so our expectation is it should not be, that is the particles present in them, they should not be when we are saying that it is heterogeneous in nature, they must be visible, because in true solution it is homogeneous and we cannot see any particles in true solution, right? So yet the dispersed particles present in them, they are not visible to the naked eye, but that does not mean they are true solution. Okay, so they appear as homogeneous, so their appearance is like homogeneous, but that is actually not true. They are not homogeneous. So if you are seeing some solution as if it is clear, you are not seeing any particle, it is appearing as homogeneous, but it is not necessary that it will be heterogeneous, because when we use ultra microscope, then you can see the particles, but in true solution, even in ultra microscope, you cannot see them. So this is because colloidal particles are too small to be visible to naked eye, but that does not mean they are homogeneous. Only their appearance is like homogeneous, but actually in practical they are heterogeneous. Filterability. So can we filter them? Due to very small size, colloidal particles pass through ordinary filter paper. It is just like the true solution property. But if you take suspension, suppose sand particles in water, you can easily filter them out. But there is another type of, that is, instead of filter paper, if you use any animal membrane, now the pore size are very small. So for this type of ultra filters, you can retain them, because now the pore size is very small, unlike filter paper. So that is why now we can filter colloidal particles. But if you take true solution, even after using this type of membrane, we will not be able to filter it. But in case of colloid, it is possible. Colligative properties. Colloidal particles, we know, bigger aggregates. So number of particles in colloidal solution compared to the true solution, it will be obviously less, because size is large. So because of this colligative properties, their order will also be small, because colligative property is totally dependent on the number of particles. So if number of particles are less compared to true solution, so compared to true solution, now colligative property, that will also have small values. Number 5th point, color. Now this is very important. The color of colloidal solution depends upon the wavelength of the light scattered by the dispersed particles. Now the size range, as we know, 1 nanometer to 100 nanometer. So there is a range 1 to 100. Now what is the size of colloidal particles? Depending on that, it will match with the wavelength of light. That is different particle size. It will be interacting with wavelength of the corresponding size. That is, there must be matching. Otherwise, scattering is not possible. So it depends what type of color we will actually see. That depends on the wavelength of the light. That is, which wavelength is actually scattered by the dispersed particles. So basically, it depends on the colloidal particle size. So when the particle size is very large, obviously longer wavelength light will be absorbed by them, and if longer wavelength light is absorbed by large particles, obviously the transmitted light, that will be shorter wavelength, right? Now what is example for this? See, here we have taken silver colloid. Particle size, diameter of the colloidal particles, we are gradually decreasing. So here size is maximum 15 into 10 to the minus 10. This part is same, so just focus on these digits. It is gradually decreasing. So when it is decreasing, this is the corresponding color change. So when the particle is maximum in size, the color that you are seeing, violet, then purple, then orange red, and gradually orange yellow. Fine. So we know that violet color, that is actually very short wavelength if you compare with this. Okay, but in case of large particles, you are seeing this color. Why? Because see, large particles absorb the light of longer wavelength. So longer wavelength light that is absorbed. So obviously the remaining wavelength that will be transmitted, they will have shorter wavelength, and you will see the color of that transmitted light. So that is why it is the light that you are seeing, the color that you are seeing, that is for the transmitted light, and it is of shorter wavelength. So higher is the size of particle, shorter will be the wavelength of light that you will see from that, for that particle. Okay, and the last important point, the color also changes with the manner in which observer receives the light. Okay, so from which side you are actually looking to the colloidal solution, that is also important. So first of all, try to remember all these processes, though all of you must be knowing this, but still we will see here what is the difference. So this is reflection. Absorption, obviously it is it will not pass through it. Okay, transmission means this is transmitted light. So see, this line is written, larger particles absorb light of longer wavelength. So longer wavelength will be absorbed, and the remaining wavelength, that is of shorter in size, they will be transmitted. So this is transmission. And scattering is like this. It is also just like reflection, but reflection is not reaching to the other side, but in case of scattering, it is reaching the other side. Okay, so the color also changes with the manner in which observer receives the light. Here we have example. So suppose we have a mixture of milk and water. When you are viewing by the reflected light, okay, so if we have a glass of milk and water mixture, suppose the light is coming from this direction, and if you are looking, that is viewing from the reflected light, okay, so if the light direction is here, your eye position will be here. So if you are looking to the milk water mixture, it will appear blue, but when you are viewing to the transmitted light, then it will be red in color, because when your direction of eye is here, okay, then you will see different color, because here the wavelength that you are seeing, that is basically the rest of the wavelength that is not absorbed. But when you are seeing from reflection side, here obviously this transmitted wavelength you will not see, so the color will be different. Okay, so these are the important points related to color for colloids. Now this property is very important, which is only possible for colloidal solution. Okay, and this is optical properties. It is not observed for true solution or suspension. It is only for colloids. So this type of observation all of you have seen. So here we have some dust particles which is suspended in the air, right? So here the sunlight is scattered on these dust particles, and this type of observation is actually known as Tyndall effect. When an intense beam of light is passed through colloidal solution in glass vessel placed in the dark, then the path of light is clearly visible due to scattering of light. So in this first beaker, the light is coming from this direction. You cannot see the path of the light, right? But because this is a true solution, completely homogeneous, but this is not true solution, this is colloid. So that is why now you can see the path of the light. Now why it is possible? Because here the particle size compared to true solution, particle size comparatively larger. So that is why scattering is possible, because the light that is coming, it is the wavelength of that light, it is matching with the diameter. Fine. So here also, this is example, we have taken some solution in glass vessel, but that is not necessary it has to be glass vessel. This type of observation also you can see. So here dispersion medium is air basically, okay, and better we say vacuum, okay. So in air, these dust particles, they are acting as dispersion phase. So this is also example of colloid, and this part of this type of picture that you are seeing, that is because of this scattering. But suppose if the dust particles are not present, then this type of observation is also not possible. Now what are the conditions that to be satisfied if we want to observe Tyndall effect? Diameter of the dispersed particles is not much smaller than the wavelength of the light used. So if it is very small, there will be no matching. Then it will be just like the true solution, because in true solution the size is so small, the wavelength will not match. So here diameter should be close to the wavelength of the light used. And the second point is refractive indices of the dispersed phase and the dispersion medium, they should differ greatly in magnitude. Now refractive index means it is the ratio of velocity of light in vacuum divided by the medium, and mostly this has different values for different materials, right? And we know that in vacuum the light, its velocity is maximum. So if we take the speed of light in vacuum and speed of light in any other substance, so this ratio, it will always be more than 1, right? Now higher refractive index means what? The velocity of light through this material, that is very low. So in this way different refractive index we can get, and here the refractive index for this dispersed phase and dispersion medium, this value should be greatly differ, okay. Cause of Tyndall effect, they are not large enough like suspension particles, because in suspension particles what happens, there is complete reflection of light, okay, and they are not so small enough like true solution, because in true solution the particles are so small, they completely allow the light to pass through them. But in case of colloidal particles, the size is actually intermediate compared to suspension particles and true solution particles. So as a result, there will be scattering. They scatter part of the absorbed light from their surfaces in all directions. So that will cause scattering of light. After optical properties, now we will see mechanical properties, and this property is known as Brownian movement. So this type of movement is very specific for colloidal particles. So when we see colloidal solution under ultra microscope, because with naked eye you cannot see the particles, the colloidal particles are seen continuously moving in a zigzag path. So if you look at this picture, as if this is the starting point and this is the ending point. So if you follow this path, this is so zigzag in nature, there is no proper pattern, fine. It is discovered by Robert Brown, so that is why the name is Brownian motion. When he actually, the first observation from which he has made this conclusion that this type of movement is there, the first example that he has seen is pollen grains suspended in water. They exhibit random zigzag motion, just like this. So this continuous zigzag motion of the orbital particles in the dispersion medium in a colloidal solution, that is known as Brownian movement. Here we have a small video also from which you can understand different colloidal particles. Here we have total 4 to 5 colloidal particles, how they are moving. Next, this Brownian motion, it is independent of the nature of the colloid, okay, but it is dependent on the size of the particles. and also here viscosity of the solution matters. Smaller is the size, lesser will be the viscosity, and when viscosity is very low, motion of these particles will be very high. Now viscosity means the resistance of the that it is a liquid property, that is fluid property, sorry. So viscosity means the resistance towards flow. So if I am saying that any substance it has very high viscosity, it means that it will not flow easily. For example, water and honey, if we take, water is much less viscous compared to honey. So if the viscosity of the solution it is very lesser the viscosity, faster will be the motion of these colloidal dispersion phase particles. This movement plays important role in imparting stability to a sol. So because of this type of motion, what will happen? They will oppose the gravitational force, because when we are saying that the sol is stable, that means what? The particles are not settling, right? So if they are not settling, that means their gravitational force, they are opposing the gravitational force. That is why they can move, they are not settling. So this type of movement, it helps them to overcome the gravitational force which is acting on these particles, and as a result they will not be settled. Okay, so this is important importance of Brownian movement, how it is helping in the maintaining stability of the sol. Okay, so that is about the Brownian movement.